afternoon, everyone. It is freezing in this room, but I have no idea how to increase the temperature. If you have any idea, go for it. Do whatever you need to. Okay, so this Wednesday we will have our second practicum. I hope your homework is going well. We will have the same setup. I will send an announcement to remind you where to come and what to expect. It's going to be pretty much organized as the first practicum was. And then next week, we are basically in the week before the fall break, which is kind of wild to me. The time has just gone so fast. And the plan is on Wednesday next week, we'll have our midterm here. I still need to check whether I reserve the other room and whether I want to split you, but I will let you know. And for the midterm, what you can expect is multiple choice questions. So pretty simple format. And some of those questions will be such that you have only one correct answer, and I will tell you, okay, there is only a single correct answer. A smaller fraction of them will be with multiple possible answers, correct answers possible, and I won't tell you how many. So that's going to be a slightly harder portion of this multiple choice questions, but honestly, just the fact that this is multiple choice questions is already much easier than this could be. In terms of preparation, I will ask you only the things we have covered here in lectures. So slides and recordings are a good way to prepare for the exam. You should go and revisit, especially bits and pieces that feel maybe like you didn't quite get them the first time we talked about them. And that's about it. I will give you maybe like 4 examples of kinds of questions I might ask you, but there won't be any practice exams because this is not like calculus. We're not learning limits and now you need to practice until you master the skill of calculating limits. This is just purely about knowledge. And there is as much as these one can make before I make them extremely hard, right? So that's why there won't be any practice exams, because going over the slides should be completely sufficient preparation for the exam. And you will need to bring your ID as always. We're going to check that. And I believe that's all I have to say about it. Yeah.
Is today's lecture going to be the last one in terms of content for the midterm, or will Monday's lecture next week also have content?
Yeah, on Monday, I will probably take a portion of that lecture to just wrap some of the things we want to finish today, and that can appear on the exam as well. The other part of Monday lecture will be kind of, let's review materials together. And in the past, I did prepare a presentation, and I feel like that format doesn't really work. So what I'll have you, I will send you the form this week where you can submit your either questions or, okay, can we go over this piece of the, content again, because I didn't quite get to what we were doing there. So I'll kind of see amongst you what are your weak points basically, and I want to focus basically half of the Monday's lecture going over those things. All right. So you should expect that soon as well. Okay, so there is that. I want to continue with where we left off last week. Are there any questions before we go further with the content? All right. Okay, so I just want to, we talked last week about neural language modeling, and the last layer to that was that now we have some representation of the decoding step and some recent history. How can we actually display a word? And remember, before we actually display the word, we had this vector, which is the vector of the size of the vocabulary with values up to 1. That altogether sum to 1. And I keep calling this a distribution over the vocabulary. And then I said, okay, there are a few options. The simplest one was to just do greedy decoding, meaning every time you display the most likely word, which won't be great for generating diverse, rich language. So we were looking at some other possibilities. One of them was beam search, where basically we always keep a certain number of sequences, which is determined by the hyperparameter number of beams. And if the number of beams is 2, we would always keep 2 most likely sequences up to that decoding step. So basically we would see, given our current options, if we extend those 2 previously stored sequences, what would be the probability if we extend those sequences with other possibilities? We would rank them by their probabilities, and then we would keep only the 2 most probable ones. And remember, probability of sequence is defined by the product of probabilities of each decoding word. But then even that had issues, namely with repetition. And I talked about how human language isn't, we don't use just the most probable words all the time. And at the 2020, we wanted something similar from language models too. We wanted to see some creativity and diversity in their outputs. And this is where we started to sample from this vocabulary distribution. And if you were to do sampling really naively, just by sampling from that whole vocabulary distribution, rarely, but sometimes very low probability words would be sampled. So if you sample lots of times, even if the probability of something is only 10%, eventually you will show that word. And that's unwanted because even though we people do use low probability words, we still know when word is, when we can use it in a given context, right? So we don't want to always sample just naively. And one thing I skimmed over last time is temperature scaling. I didn't skim over it because it's unimportant. If anything, it's really important, and I wanted to give it more time today. This idea is simple, but quite useful. Similar to softmax, you can use it for various things. Here, we are just going to adjust our softmax equation by introducing this hyperparameter called temperature, denoted here with capital T. So you basically divide both your numerator and every factor summed in your denominator by T. And T is going to be low. We will choose it to be low when we want to sharpen the probability. So here, in this situation here, I will go to the previous slide. You had nice dog car, and car did receive some probability, but we actually never want to sample car because it has such a low probability. And we deem that it did receive some probability by the model, but we never want to sample such low probability words. So by introducing lower T and dividing each factor in our softmax, basically you are going to sharpen the distribution. So car will receive even less probability than it had before, and nice, which had higher probability, 0.5, will receive even higher probability. And then higher T will result in softening probabilities, which is we want to do in certain situations. So I can kind of offer this way of thinking about changing these probabilities. Sometimes you have a task where you want more deterministic outputs, but not greedy decoding. Sometimes you want fully deterministic and use greedy decoding. You always sample the most likely one. And if you give to the same trained language model the same prompt and use greedy decoding, you will always get the same outputs. And sometimes we do that, especially in research, when we want to compare to other models, to other approaches, let's say. Sometimes the application itself is where you require more deterministic outputs. So for example, maybe in medical domains, you're making some decisions and you don't need crazy creativity in outputs, and you want the model maybe to sound slightly more human-like, but doesn't need to be like super creative. And then there are applications like creative writing, where having this really funny way of sampling from these flat distributions might be kind of nice, might spur some co-creativity between the writer and an LLM. So it all comes down that we now, as we move forward and learn what LLMs are, we're also going to learn that they are meant to be general purpose and used for many applications, like ChatGPT, right? You might use it for creative writing, and you might want to use it for something which is more like knowledge question answering, where you always have the same, fact that you should retrieve. So it really depends on the application, on how you want to choose the right temperature here. Do you want to sharpen or flatten the probabilities? Okay, so then I also said we want to restrict the choice of plausible, kind of like a plausible set of tokens to display. And I said we could do this by choosing K, the number of tokens, top probable tokens we want to sample from. And the issue here is if we always choose the same K, no matter where in our decoding we are, sometimes we'll have sharp and sometimes we'll have these flat distributions. So here, where I have a sharp distribution, I have chosen very high K for that situation. And I have included in my set of plausible tokens that have really, really low probability of, I can't really tell, but you can see how small these bars are. And this is how this problem is then addressed by introducing nucleus sampling, which instead of always fixing the same K, the same number of tokens to sample from, it's dynamic. We choose the number of most probable tokens that together have a certain probability mass. So here, a lot of them have probability mass and all of them have individually enough probability to be sampled. And however, here, only the first most probable 3 tokens together already give us probability mass of over 97%. So now we restricted it, and our plausible set of tokens to sample from in this case is only 3, where here is much more than 3. Okay, so this is what we talked about last time. And then one thing I want to mention, there is a lot going on this slide, and this is more like a reference point for you. But today, when we are using APIs for large language models or Hugging Face ecosystem, which we are going to talk about more for working with open source models, you are going to be setting these hyperparameters, temperature and top P yourself. And there are some default hyperparameters out there already. But very often people will combine the temperature and top P, and you might ask why do we need to both? And the idea is that they have their complementary features. So temperature will reshape these relative probabilities. It's going to basically, we are working on how sharp or flat these distributions are going to be because we know what kind of application are we working with. So we already have a notion, oh, I don't want a lot of randomness, so I'm going to sharpen everything. Or on the other hand, you might be, oh, I'm doing something really creative and I want actually a lot of randomness in outputs. Once you set that, then you use nucleus sampling to basically fix this plausible set such that you really don't sample those really low probability tokens that can still survive the temperature rescaling. So basically together, they give you kind of a lot of control. Okay, any questions about sampling before we go into the intrinsic evaluation of language models? Yeah.
So do you apply temperature before copy? Do you apply the scaling?
I think that's how it is implemented. Honestly, I don't know this detail because we are going to work with the libraries which implement this for you. Namely, are going to use Hugging Faces transformers, and then you have this function called generate. So write model.generate temperature equals top equals. And now, although I've used it so many times, I don't know how exactly that it's implemented. But what you said makes sense intuitively, right? Like we first rescale it, and then we do the nucleus sampling. Yeah. Okay. Okay, so I just want to re-emphasize that this is a really important topic, how to sample from the distributions. I introduced it pretty early on because you do need to sample from language models. And before 2020, we didn't use nuclear sampling because it didn't exist. The publication was released only 5 years ago. But I think it's already, we are at the point where we need to think about, okay, I have produced a distribution over the vocab, what now, right? And you have all these options. But this general purposeness, I think, will connect with you only when we start to talk about large language models more. Okay, so remember that I told you that NLP models, and I mean in general, machine learning models can be evaluated by their intrinsic value and their extrinsic value. Intrinsic means we are evaluating, just to repeat, how good the model is for the task we developed it for. But very often in NLP, we do create models to be then getting an artifact that we are going to use in the next model. So previously, we have used skip program model to produce word embeddings. And then we use those word embeddings to plug them into a classification model to improve the classification performance. Their intrinsic evaluation was the word similarity correlating with human judgments of word similarity. And the extrinsic evaluation was, oh, do I improve the classification performance once I plug these models relative to the, when I plug these embeddings relative to some baseline. Here, similarly, I won't talk yet about extrinsic evaluation, but remember I have given you applications in mind, such as detecting texts with errors, like grammatical errors, was one of the application areas of language models, because you can calculate the probability of a sequence, and maybe if it doesn't reach some threshold, you can say, oh, it might have some mistake. That would be like an extrinsic evaluation of language model. You can do that and then see again whether it improves over some grammatical error detection baseline. But more importantly for us now, because we are going to talk a lot about language models and how to use them for various applications, and every application from QA, summarization, translation will have its own evaluation measure. Here I want to focus on intrinsic evaluation. And our goal for designing language models is to produce a model that can model the probability of a sequence well. And probability of sequence is defined through chain rule as probability product of conditional probabilities. So it also needs to do conditional probabilities really well. It's like, if it does that well, then it can do the probability of the entire sequence. So our language model, if we use some data to train it and or count the relative frequencies with statistical n-gram LMs, once we do that, we can take a held out portion of our corpus, so portion that we didn't use to train the model or count a relative frequency, and we can see what the likelihood of that corpus, of that written text, is under our language model. Right, so our language model is calculating probabilities, and as a sequence of text, we can give it a held out text and see what its probability is. So that's basically what we are going to do, with a slight tweak that's just, I would say, historical, comes from history of how these models have been evaluated and where some of these probabilities ideas come from. Namely, information theory, we talk about surprisal, whether the piece of information surprises you, right? So here we are going to take the likelihood, the probability of seeing our held out written text. And we are not going to report that, but rather we are going to take the inverse, such that higher likelihood means lower perplexity. So if you have given high probability to held out text, which is good, it would mean that your language model is not surprised by that text, which is good, right? Like if the language model is good at modeling that text, it shouldn't be surprised by it, right? So we are just, this mathematically might look scary to you, but it isn't scary in a sense that we are just talking about this in a slightly different way. Instead of saying, oh, the written text has high probability under language model and it should have high probability, we are going to say, oh, the language model isn't really surprised by this text, which is expected. And then we also have this nth root, and the only reason why we include that is notice that the length of our sequence is n. So it's used to normalize the measurement by the number of words. Otherwise, because remember that we are calculating the probability of sequence by multiplying these conditional probabilities. Each probability is numbered between 0 and 1. So more such numbers you multiply, the smaller the entire probability is going to be. So you would penalize longer pieces of text if you didn't use some normalization. And this is where this nth root comes in to normalize by length and not give smaller, unfairly small probability to longer sequences. Okay, so again, this is an intrinsic evaluation. It is mostly used by researchers who want to show that their language model is better than other language model in language modeling. What we actually care about is extrinsic evaluation, which I won't cover now because, as I said, as we start to talk about large language models and how we can apply it for retrieval augmented generation, we are going to talk about these measurements for evaluating RAG systems. There is also not ideal number to be here to be reaching. So if I, give you a homework and I tell you to train an LLM, report perplexity, your natural question might be like, how do I know it's good enough? Usually I do give you some thresholds so you know roughly what to work with. But there is a magical number here. You will see typical perplexity values ranging from 10, 20 to 200. So if you are way above this range, maybe typically if you have like perplexity of thousands, like okay, this something has gone wrong either with the perplexity script or with the language model itself. And the last thing I want to emphasize is that to compare two language models and their perplexities, they need to have the same vocabularies, right? Because in the end, we are measuring the distribution over the vocabulary. And now if one vocabulary looks like 10,000 tokens and the other one is 100,000 tokens, well, of course, these probabilities will look much different and the probabilities of sequences. So it's kind of comparing apples to oranges. So only when two LMs have same vocabularies, we can compare their perplexities. Do we remember what determines our vocabulary? How do we produce it? When do we produce it? Yeah, we take it from the corpus. We take it from the corpus, but what do we do then? Like we have corpus and tokenize it with each token. Exactly, each unique token, which I didn't say, but you will see term types used for it, like unique tokens in the vocab, is placed in the vocabulary. So tokenization determines what is the vocabulary, right? If I use white space tokenizer and I use smarter word like a tokenizer that's going to separate words from the punctuation symbols, for example, I will have actual punctuation as vocab tokens, right? So tokenization determines the vocabulary. So if you use different tokenizer, typically you can't compare to LLMs. And when we move into LLMs, almost none of them have shared tokenizers and therefore not shared vocabularies. And therefore we can't compare their perplexities. All right, anything unclear with that? Okay, so now we are going to move forward. I did say something like that. Okay, so now we have talked about neural language models, very simple one, already like over 12 years old. And we are going to now move towards talking about these sequence-to-sequence approaches and neural approaches to them, which taken one sequence, they produce another sequence. And this is all going to then build up to our transformer architecture. So basically last lecture and today's lecture is all we are going to kind of, it's going to prepare us to talk about that transformer architecture, which is the neural architecture we use to this day, and is the basis of most large language models. So let's get started. Okay, to motivate sequence-to-sequence approaches, I'm going to introduce briefly the task of machine translation. So machine translation is one of those holy grail problems in AI, and it's one of the oldest NLP tasks. The setup is pretty simple. You have a sentence in source language. Now pay attention to these terms. I'm kind of putting in bold in my slides. So we always say this is a source sequence, and then there is going to be target sequence. For example, here we have a sentence in Croatian saying danas ćemo naučiti o strojnom prevođenju. And the goal is to translate that sequence into the target language, for example, English. So produce a sequence, token by token, saying, today we will learn about machine translation. So pretty simple. And I think because we all use Google Translate when we travel, we are pretty familiar with this kind of technology. To train machine translation, you need a so-called bytext or parallel corpus, meaning you need a source sentence aligned with its parallel sentence in another language or target sentence. Translation produced by human annotators or target texts produced by human annotators are called reference translations, and machine translations are called hypothesis translations. This is also a very important terminology because when you start using libraries, you will see references and hypotheses. So you will need to know, oh, that refers to human-authored gold target versus the generated one. Okay, so why is machine translation hard? Well, it requires a lot of rewording, reordering, and rearranging words, replacing single words with multi-word phrases, and so on. So, for example, here we have a sentence, Croatian, kako se osjećaš? Literal translation would be, how do you feel? And then if I did reworded translation of how are you doing into Croatian, which is called back translation, I would get kako ti radiš, which if I then literally translate it would be how do you work? So it doesn't work, right? Like if I go back to from English to Croatian. We can have jučer sam kupila knjigu. Literal translation would be yesterday I bought a book, and reordered translation I bought a book yesterday is what I get if I back translate the yesterday I bought a book into Croatian. So again, just doesn't quite work. And then like changing multi-word phrases with single words. So here we have mašina za prašnje posuđa. Literal translation would be machine for washing dishes, which we all know and like to call dishwasher, right? So sometimes you can't translate word by word. You need to know that these 4 words together are actually need to be translated with a single word. So it's not simple. There are a lot of, if you would develop a rule-based systems, there would just be so many exceptions because there aren't these, word-to-word alignments possible. That said, people in the beginning did try to build these word-to-word models where you are trying to align which word in a source is connected to the word in a target sequence. And then if you have bunch of words, you can say, well, I'm going to align these source words to this one and not to the other, and so on. So if you know how to learn the word alignment, you can maybe solve a fraction of these translation. And I won't go over this if this was if we were learning about machine translation before we had neural models, then we would go in depth of this and wouldn't be simple. We would use an algorithm called expectation maximization, which Vivek maybe teaches you in machine learning. And if you have, learned this algorithm, it's not super trivial. But the idea there is basically, okay, I have this parallel corpus of sources and targets. So I have a bunch of information when a certain word is, connected to another word in another language. And I can use these occurrences, co-occurrences to my advantage to then predict, oh, if I have a new source sentence, and if I go word by word, like I can predict these alignments. But you will need to train such a model to be able to do that. And as we have just seen in previous example, the issue here is that very often you can't translate one word to another word one by one. So with the dishwasher, that's a single word in English, which was 4 words in Croatian. So I have another example here. So idemo na kavu would be translated, we literally translated to we go to coffee, obviously ungrammatical. Maybe something you can say is like, we'll have a coffee, and then you have 3 words for 2 words in the source sequence. So basically the phrase-based translation would generalize word-based models by having these, not learning only, learning when 2 words need to be matched with 3 words and arbitrary number of those. And of course, you can imagine this is getting more and more complex. So these, again, algorithms aren't super simple. But people have been working for them for a really long time. And then in 2014, the field has dramatically changed by neural machine translation. So it was very, very important in NLP and neural ML, which is, maybe when you learn about it for the first time, it sounds slightly complicated, the neural architecture. It requires so little human intervention in the sense of building features and making rules and so on. It learns from the data, and it had achieved at the time very, very big improvements over the basics. So today we are basically going to go into how to use neural networks for modeling neural machine translation. And we are going to go over the Bayes approach. And then I'm going to mention some issues with this Bayes approach. And then we're going to talk about attention mechanism, which will help us fix that issue, whatever it is. And then that attention mechanism is going to be really important when we move to transformers, because the key component of transformer is self-attention. So already you hear attention and self-attention. So there will be some similarity in these concepts. And then if you remember when I gave you like a preview of topics we're going to talk about 2 weeks back or a week back, I don't remember, I have said that transformer, specifically self-attention, will fix a lot of issues. So it's going to be a major, advancement in architecture, which will give lots of advancements in downstream applications. Okay, so let's get started with this. Any questions? Yeah, please.
Think of what's on the website, the course website, because it would be really helpful.
Should I put it now?
Yeah. Thank you.
Sorry about that. Yeah. Let me do it. All right, that should work now. Let me know if not. Okay, so first of all, sequence to sequence. What does this mean? You might recognize this name, Ilya Sutskever, from OpenAI, not anymore in OpenAI. Anyway, he is the first author of the paper that introduced this sequence-to-sequence approach, which is a neural approach that produces a sequence given another sequence, as the name suggests. And this is an example of what in NLP we would call conditional text generation or conditional language model, because you're producing a target sequence given some source sequence, right? Originally, it was approached with a neural architecture called an encoder-decoder. Again, when we start going into the details of transformer architecture, I will teach you an encoder-decoder transformer. Then I'll tell you, well, in 2018, we said, let's just use an encoder transformer. Then we went back and for a year did encoder-decoder transformer. And then when GPT-3 was released in about 2020, we switched to decoder-only transformer. So we are going to talk about all these versions, but initially I'm going to introduce it as an encoder-decoder architecture, and just going over it today with another type of neural architecture is going to be helpful when we get to the transformer. An encoder takes a variable length sequence as an input, and it's going to transform it into a hidden representation, meaning a vector of a fixed size, right? So we have arbitrary number of source token. In the end, we are going to get a vector representation of whatever is the hyperparameter we set for the size of that vector. And then decoder is going to take that vector where we kind of capture the linguistic phenomena, hopefully, of the source sequence. And then it's going to act as a language model. So given that vector, it's going to produce a next token and the next token and next token. So this is where our knowledge about language modeling comes into the play. Originally, encoder and decoder are implemented as recurrent neural networks. I will introduce them today similarly, but it's not of practical importance. We are going to introduce it like this just so you get to use these mechanisms of encoder, decoder, encoding a sequence, decoding a sequence, and so on. But as soon as we come from the fall break, we are going to talk about transformers and do this with transformers. Okay, well, forget about this. I think this was from the last year. Remember when I said seq2seq won the best test of time award at NeurIPS, our flagship machine learning conference in 2023? Well, in 2024, last year, sequence-to-sequence, this specific paper also has won test of time award. And I kind of like that I have this snippet so I can share with you why the larger community and experts in the community think this is the paper that 10 years after has such a significance. So it says by NeurIPS's award committee that sequence-to-sequence learning with neural networks has been cited more than 27 times as of this blog post. With the current fast advances of large language models and foundation models in general, making a paradigm shift in AI and applications, the field has benefited from the foundation laid by this work. It is cornerstone work that set the encoder-decoder architecture, inspiring later attention-based improvements, leading to today's foundation model research. Okay, so this is why we are going into this work before we start talking about LLMs. All right, so here is a visualization of RNN. It doesn't matter what it is right now. I'm going to use the whiteboard, but I think this visualization is going to help you for a second. And I'm going to derive what this sequence-to-sequence approach for neural machine translation is on the board. So we have neural machine translation or seq2seq. Not really or seq2seq, it's kind of separate thing. I shouldn't say, I suggest they are equivalent. I will say neural machine translation with seq2seq. Okay, so this is going to be another example of supervised machine learning, but generative machine, right? You're trying to generate data instead of classifying. So our data is going to consist of pair of a source sequence, S1 to SL, together with its target, let's say, translation. So T1 to DK. You might be noticing that I keep saying translation and then I kind of switch to generation. And this is because I'm using neural machine translation as an example of sequence-to-sequence text generation. But many tasks can be approached like this, such as summarization, where given a source document, they're trying to produce much shorter summary. Or like ChatGPT, right? As you have interactions, right? Like assistant user, that's the source, and then you're trying to produce the next utterance, which would be target sequence. So seq2seq, it's used for many applications, but today we are using neural machine translation as an example. So you have a pair of source and sequence tokens. So these are tokenized source. And this would be tokenized target here. And then my data, of course, won't consist of just a single example. It's going to consist of n of these. So we'll have I equals from 1 to n, and I'm going to add superscripts here. So that's the data. Now, my goal is, as always, to maximize the log probability or minimize the negative log probability of seeing the targets given the source. So that's my goal. I'm trying to develop a neural network that's gonna do that. Okay, and my approach is going to be to use sequence-to-sequence approach. Namely, given a sequence, I'll try to generate a sequence. And I'm going to use as a neural architecture this recurrent neural network over there. All right, so let's go over some notation before we start to look into the architecture. Is this one dark enough? Do you see this color well? Could be better. Yes. Start with this blue one. How about this? This is better? Okay. All right, so I'm gonna introduce all the weight matrices we are gonna need. So my encoder will I will show you how to build 2-layer recurrent neural networks. So we are going to have here encoder 1. This denotes the layer. This denotes that this weight matrix is gonna appear in the encoder. And this one, I can't tell you yet what the subscript mean, but it will become clearer when we are starting to write equations. So this one is going to encode the source history. So if I am at the token number 2, my history is only the token number 1. And this weight matrix is going to help me remember that previous token. And then if I'm at the token 5, here, this matrix is going to help me remember, or not remember, but rather kind of inspect the representation where 4 previous tokens and their features have been captured. All right, so then W2 encoder first layer is going to be, I'm going to write this in the first layer. This one is going to encode the current token in the first layer. Then I'll have similarly for decoder. In layer 1, I'm going to have a matrix that is going to help me encode the decoded tokens so far in the first layer. And it's going to help me also the other matrix for the decoder. It's going to help me represent the token, the current step. At the current decoding step, whatever that token is going to help me with that one. So it's going to help me encode the token in the current decoding step. Step in the first layer. So now I'm not going to repeat this for second layer. So here we would change 1 to 2, and that would just indicate that I'm doing these operations in the second layer. Yeah, I'm going to use this one, which is not super visible here. So this indicates layer number 1. Okay, so that's our setup. Let's start to decode stuff. What is here? Okay. Okay. Oh, sorry.
So we want the decoding ways to decode that encoded, or is that just confusing?
If it's confusing, that's okay. Let's work through the equations, and I think some things will become clearer once we start to transform the vectors.
Okay.
And then we will revisit whether it's still confusing after that. How about it? Okay, so the first part of the decoder architecture is going to be encoder. And then in my previous slide, I had said that that means that I will take my source sequence and I'm going to produce one vector that should represent that whole source sequence. But the way I'm going to do it is it's visualized here. I'm going to start with my first token in my source sequence. I'm going to transform it, and then I'm going to go to the next token, and I'm going to consider the representation of the previous token and to produce the representation of the next token, and so on. And at the end, I should have a representation that captures the entirety of the source sequence. And that's what the encoder does. So the encoder is not yet producing any text, okay? Because it is there just to find a vector representation that captures the information in the source sequence such that we can do decoding. So here, we just want to produce the final vector, a step by step going over these tokens. So let's say we have a source sequence. So source being a tokenized sentence. So how are you question mark? And I'm going to add here pad just to get you used to it. So imagine we are doing this, we are implementing this now with your homework, you're aware of like importance of batching. If I have these variable length inputs, I don't want to encode them all one by one. Remember, if we can do something in parallel in this world, we will do it, right? So we can encode multiple sources together if we pad them to the same length, which is usually the length of the maximum length observed in a batch. And usually this pad is going to be set to 0 vector, so all the subsequent computations with it will result in a 0, and is basically nulled out in the computations. Okay, so we have this sentence, and our goal is to go from English to translation, to Croatian. The first thing we are going to do is we are going to take the first source token, and our goal is to produce a vector representation of it. So I'm going to start, as always, with an embedding of this token, and I'm going to remember I used else's to denote source sequences, but I'm going to introduce this notation ES1 being embedding of source token number 1. Then my first operation will be as follows. I want to produce a hidden representation S1 of this token, source token 1, in the first layer of this architecture. Oh, this is going to be complicated. It's weird. Okay, so I'm immediately gonna introduce ReLU because we are going to do nonlinear transformation as always. And this is where things get a little bit interesting. So I want to use 2 weight matrices, one which will, as always, linearly transform the current vector, so current representation. So current representation of my first token is the embedding, right? And I'm just going to linearly transform it, and then ReLU will non-linearly transform it. But here, I'm also going to introduce a transformation of the history. So this is going to be W1E in the first layer, serves to transform the history, which is here denoted, and I didn't introduce this, age as 0. So in here it's weird because we are at the first token, so we don't really have history. So we are going to initialize some hidden representation with zeros. And we are going to say, you are my initial history, a 0 value, right? And I'm going to linearly transform my current history, which is right now 0 because we're starting. And I'm going to add it to the linear transformation of the embedding of the current representation of this token. And that's going to become my representation of the first token in the source sequence. Now, if I want to do another layer, so for the same token in the second layer, I would again transform the history using appropriate methods. And I would transform, but now here we need to be cautious. Remember, when we are using deep learning, what do we use here? Remember that slide where I have a bunch of equations stacked with some nice, like, dynamic visualization of how the space changes from something that's not linearly separable to something that is linearly separable. So what do I need to add here? If I'm just at the second layer. Yeah. Yeah, exactly, right. We have produced some representation of my first token, and now I'm at the second layer of my neural network, which just means, oh, I want to do another transformation of what I have produced previously. So here we would just add H, S, 1, and here 1 coming from the previous layer. And that's my current representation. But that's my final actual representation because I'm just going to use 2 layers of the first token in the source sequence conditioned on history, which is empty, right? Now we are moving to the next one. So we have we embedded second sequence, a second token in the source sequence, excuse me. We transform it similarly. So age of S2 is going to be ReLU of transformation of the history. And now this is important. First, I'm going to keep everything layer-wise. So here, I'm going to use representations coming from first layer if I'm going to reuse them from the history. So again, I use W1 encoder, first layer, to transform my history. And this is where I assume that entire vector HS1 in the first layer captures the entirety of the history. So HS1 in the first layer. So see, here we have 2, and here we have 1. Plus W2 encoder 1 of H, excuse me, this is my mistake. Of the current representation of this token S2. So what should I use here?
Embedding of S2.
Embedding of S2. That's it. And then to produce the representation of the second token in the source sequence in the second layer, I would use again W1 encoder in the second layer of HS1 in the second layer plus W2 encoder second layer of HS2 from the previous layer. So this one is going to be used here, right? And then this one here is going to be used here. So because we are at the beginning, I will write this just one more time for the third one. Embedding of S3. So here, when I'm using the history, I'm going to use the representation coming from the first layer of the previous token. But notice that we actually have 2 previous tokens. And the reason why we do that is because with this neural approach using recurrent neural network, we assume that HS2 is here. HS2 is remembering somehow features of the current token, second token R, as well as the previous token H. So because you are taking these representations, and then you are one by one changing them as you see next token in the source, the idea is basically that you are starting with some history vector and you are changing its feature based on all of these tokens in the source. So when we come to our last tokens, we have them 1, 2, 3, 4, 5. Fifth token, when we have produced the HS5, the first layer, or HS5 in the second layer, we assume, because this is the 5th token, right? So we have 1, 2, 3, 4, 5. When we have encoded our 5th token, we assume this is the vector representation of the entire sequence, okay? And again, I will repeat why we assume that. We assume that because we start with HS0 as history, then we change it. HS1 contains information about the previous and the next one. And then the HS2 is getting some information about the previous one. and the current one, but the previous one recursively think, it has information about previous one and previous to the previous, right? So when we're at the fifth step, that's why we deem that now we have information about the current one and the previous one, but the previous one had information about the previous and previous and so on. And in this way, you have captured the history. Yeah.
With this sort of recurrent model like this,
Mhm.
are there any sort of diminishing returns on history for information from way back when? When we have all
Yeah.
these hidden vectors that are relying on information from this one, and then that vector is relying on the other one, how much of that might get lost in the process?
Lost a lot. So in theory, nothing about recurrent neural network should lose information. In practice, we do see that, and there are newer versions of RNNs called LSTMs, but even they have complications. And this is why these architectures aren't the architectures we are using today, but rather transformer. So there is definitely issues with these. But it does help us first think about how we move. Remember previously when I taught you neural language models, and I said, well, you somehow need to capture history. And there we had this sliding window of fixed size number of tokens, which we will set to 5, right? Here we are trying to do something more clever and kind of go away from that n-gram idea where you have to look only at a few previous one. And instead, you are trying to capture the entirety of the history. So now we are moving in a direction where we are better than, n-gram and neural language models of 2003, what we can do with them. But you're right. I'll come to that there are issues to that. And then another point here with like these demonstrations with RNNs is to see these ideas about encoder decoder, because the higher level abstraction of what encoder decoder is, it's not really going to change. So to repeat, with encoder, we are encoding this source sequence. And we deem that the hidden representation produced at the last token in the source sequence is the representation of the entire sequence. So now the decoder won't change much, except that we're going to have new weights and everything. Okay. So our ground truth target here has some special things. First, we are going to start with some beginning of sequence special token that we add to, to the beginning of the target. So this is always something you will see. It kind of indicates to the model, now we are starting to generate next token, right? The translation would be C question mark. Oops, that's not a question mark. And at the end, we would add end of sequence token. And end of sequence token is there because otherwise we never would teach our models to stop generating something. So this is the way to say it's enough, right? So you'll see when we start, when we inspect a little bit of transformer library, then you have this function generate, which I already mentioned. And one of the hyperparameters there will be the number of tokens you want to generate. And sometimes you will generate more than you need. And basically what the model will learn to do is produce EOS just repeated to say like, I'm done, and done, and done, and done, and done, all the way until you actually hit the point with your for loop in the end, which says no more generation. Okay, so the actual equation here is going to be really similar, but now this is where we start to decode things, meaning we start to generate tokens. So first of all, let's start with HT1, so target. First, target token representation in the first layer is going to be, imagine I have produced the embedding, so embedding of T1, which is the embedding of beginning of sequence token, BOS. And similarly to how I considered history with my encoder, I'm going to consider my history with the decoder too. But here I'm going to use the last source tokens representation as my history. So now it's not zero, right? Like now I know something. I am going to introduce a notation somewhere. Okay, here. So my HT0, remember my HS0 was zero vector. Here it's going to be the hidden vector of my source sequence last token, which was the token at 5th position, right? And again, I have 1 and 1 just to indicate the layer. So here 2, HS5, 2. All right, so in my first layer, notice how I'm changing the superscript here from E to D. So this is new weight matrix here that is responsible for the decoder part. And this is why you can think about encoder, decoder as a two-part architecture, right? So here I'm using these other weights. 1 of HT0 initialized like this, right? In the first layer plus W2 D in the first layer of embedding of my first target token. Then I will just do one more transformation. So I would take W1 D in the first layer of HT0 in the second layer. Sorry guys, this was a mistake. Second layer now, plus W2 D in the second layer of HT1 in the previous layer. Okay, so now we have a hidden representation of the first token. What now? What was the goal here? What are we trying to do? Also, I forgot Vilus here. So we had source sequence, which was, how are you? And I'm trying to translate this in Croatian. And with my encoder, I have produced a vector representation that should capture the features of my source sequence. I have now used that information to condition here representation of the BOS token, which says beginning of sequence. So what now? What is our ultimate goal? Yeah. Actual tokens, right? But here I'm at the first token of the target, so BOS. So can you be just slightly more specific? You said given source history, we want to produce tokens, but at the first decoding step, what do we want to produce? Given BOS token, we want which token?
Oh.
Yeah, exactly. So I know this is weird. It's so given our beginning of sequence token, we want to produce next token, right? We are doing next token prediction the same way we have done it with language modeling, the pure language modeling. The only thing here that's changing is this is conditional language modeling because we are conditioning it on our history about the source sequence, right? And of course, I change also neural architecture, which didn't help for you to make the connection super easy. But now we are doing the generation, which is the next token prediction. So given that I have this hidden representation, so I have a vector. Focus only on that. I have a vector, and now I want to produce a distribution over the vocab. What should I do? So given a vector, I want to produce a vector of 0s to 1 values.
Softmax?
There is a softmax involved. What do I need to do first?
You need to do the logins.
We need to do the logits, right? And how do we do that? Yeah, dot product between what?
Source and so the source is and the weighted is.
So if I have you say I should calculate the logits by doing the dot product of being a source vector.
Which we have and the weight is which we have.
Okay, weight vectors. Let's focus on weight vectors. What's the size of the weight vectors? What's the shape of that tensor or matrix that I should use?
It's vocab by D2.
Yeah, vocab by D2. I didn't quite use any dimensions here, but yeah, let's say we have if D1 is RD1, this is going to be RD2, and actually I would transform this into another vector of size D3. So yeah, you are right. We would use a weight matrix, output weight matrix of a shape vocab size times D3, because that's the dimension of the hidden dimension, right? And I want to produce logits, which is the vector of the size of the vocabulary. And I would use the current tokens representation, H2, HD2 in the second layer, right? We are stacking the layers. So alpha layer is going to appear after the last one. These are going to be logits. And this is going to be the vector of the size of the vocab. And then I heard some softmax, right? So to get the actual probability distribution, I would do softmax of this vector of logits, as always. And then what do I need to do then? Yep.
Oh, you do like artifacts or top casing.
Yeah, exactly. Many of these options we talked about today. So here I have a distribution over the vocab, right? So if this is 0, 1 to the size of the vocab, then maybe I'll have something like this. I mean, probably not nice as this, but this is when I say distribution over the vocab, this is what I mean. And then we do sampling. So to actually get the word out, we need to sample from probabilities. Yeah.
Should that second hidden layer, is that for target 1 or target 2 for the
Oh
second?
yeah, there is a mistake there. Thanks for catching that. So P1, P1. Too many numbers. T1, T1, yeah. T0, T1, 2, 2, 2, 2, 1, 1, 1, 1, 2. Yeah.
Also, why is the dimensionality of the second hidden layer larger than the first layer? Why is it D3 and the first one is D2?
Who said it's larger though?
Oh, wait. I guess I'm just a bit confused by the notation, D2 versus D3.
Yeah.
What do they correspond to?
Symbols, right? So I'm introduced symbol D1 to denote the dimensionality of the embedding layer, but that's abstract notion. Like I don't tell you D1 doesn't mean 1, right? Like it's a symbol to denote the size of this vector. So D1, as we know, is 50 or 300. D2 might be 400. D3 might be 450.
Okay, so
But these are all
they're
hyperparameters.
just different dimension.
Yeah, exactly. So
Okay.
D1, D2, D3, so symbols for representation sizes.
Okay.
So I could have used ABC, right? Or I could say D3, D2, D1, right?
Yeah.
There is no relation between symbols.
Got it.
Okay, so now we sample this word, and this is where that idea about teacher forcing or schedule sampling or using generation comes into the play. Because when I move to the next step, now I have some word sample here. So in my target data, in my parallel corpus, next word is kako. For some reason, let's say that the word that's sampled here is što. So one translation that could be reasonable here instead of kakosi could be šta ima. That would be also reasonable. So let's say that the model had sampled što instead of kako. And now we are faced with the decision of what T2 is. Is it going to be the word we sampled, or is it going to be the word that occurred in the input? And the last time I told you, this is a choice you need to make. So typically we would use teacher forcing, meaning the word that actually had appeared as the next word at the beginning of training, because our model won't be a good model at the beginning. Or we can use schedule sampling, meaning we have a value P, and with that value, we decide which is initially, it is a value that determines whether we use this word that actually appears or the generated one. Initially, we have high value of P, so we often generate the true word, but then later in training we can lower it, which would mean that we would, with a higher probability, choose what we generated. So don't forget that choice. I know it's a little bit abstract and it seems maybe vague and unnecessary when I talk about it, but as soon as you start to implement this, you need to make that choice. So, and then you're immediately faced with, oh, what should I implement? And that's why I keep mentioning it. Okay, now I don't want to write this whole thing again, but as you can imagine, let's say I chose teacher forcing, my T2 is kako, then I would just repeat these equations, right? And I would use HT1 here instead of HT2, and here I would use embedding of T2 and HT2 in the previous layer. And then again, I would have logits, probabilities, sampling, and moving on to the next one, and next one, and next one. Last thing I'll say is, what is the loss then here? Loss, again, this is kind of lands better with implementing. So loss, as always, is going to be our negative log likelihood. So we will have negative log probability of seeing the true next token, so kako, given BOS. So true next token. And remember that this probability lives in this probability vector, right? So no matter what you have sampled, maybe you have as a highest probable word što, you wouldn't use that probability, which also lives in the softmax vector. Rather, you would find where is my value for the word kako here. And you would use that probability, apply log, negate it as your loss at that decoding step. Now, interesting here thing with language models that we didn't have with classification, we have as many of these log probabilities as we have decoding step. So you would sum or average all those log probabilities, and that would be the probability, the loss, I keep using wrong words today, the loss of your entire generation Now, given that loss, you would do backpropagation. So you don't backpropagate at every step. Rather, you calculate losses at every decoding step. You sum them, you average them, and then you calculate gradients. I mean, not you anymore. Remember, now we use backward, fancy PyTorch stuff. We backpropagate through all of these weights, right? And because there is this recursion involved, when you are backpropagating from the last step, from the loss calculated in the last step, you're actually going to go through the entire decoder and entire encoder. On a second to last decoding step, you're going to go through, the current through these representation at that token and all the previous one. And this is where these issues with RNNs appear, which are namely, you are starting to have a lot of gradients one after the other. And if soon as one of them is very low, you might get a trouble into having all of the gradients being zero and the problem of vanishing gradients. Or even worse, you can have exploding gradients where because you are having so many, your chain rule is so long, you can get very, very high value. Okay, we are going to stop here. We are going to just touch a little bit more on what these issues are. And then we are going to talk about basically make this a little bit more complicated with the tension and have the recap and then midterm.